Okay, thanks for everybody coming to my talk. So I saw about 25 audience, and some of them I'm familiar with, and parts of them I am not. So today my name is Professor Tso-Ren Wu, and I'm going to show you some of my interesting results. Including, first of all, is from the Coast to Ocean. I want to tell you something about Megathrust from South China Sea, and recently the Ryukyu change. So on this page, you can see some important information. First of all, this is my face, okay? And you can see three-dimensional simulation, like a hemisphere sliding down and the generated waves, okay, like this one. And also you can see something like a mud flow sliding down. And also you can see that there's a moving glass, which with red wine. This is the birthday gift from my student, Hu Shunkai. I appreciate he used this way for giving me a gift. So, let me start today's talk. Today I'm going to talk about the tsunami, including 2D, 3D, and also the Earth science from the Earth science point of view for about 40 minutes. And first of all, I want to mention something about recent very popular topic. One is the Nankai Trough. You might say, why starting with the Nankai Trough? Because connected to Nankai Trough, the next one will be Ryukyu change. Okay, so Ryukyu change, currently no big disaster. But that's why we were so worried about if a change has been sleep for a very long time, then sometimes that indicates that means the earthquake energy is accumulating. So here I want to show you something about the recent results from Nankai Trough, and also I can see that most of you came from Taiwan and Southeast Asia. So you might know something about famous prediction. The famous prediction is from Miss Ryu. She's a Japanese famous comics. She has a comic book 30 years ago. She write down something from her dream, and unfortunately this comic book wasn't being paid attention to people. So the comic book didn't sell very well until 2011, Tohoku earthquake happened. Then some of the readers noticed that on this comic book, it already says something about the Tohoku earthquake, and then they starting checking the detail of the comic book, and they found that she had 15 dreams, and 13 of them came true. And so So on this page, you can see that it says 2011, there's a big earthquake, big disaster happened. And so people were so scared that these things even affect the tourists in Japan. So the Japan like hotel and airline tickets are so easy to book for this summer vacation, because this book says in July 5th they will have even larger event which will affect Taiwan and Japan and the Philippines. So this is the page on the comic book. I hope you can see some details. First of all, here's Taiwan, and here's Japan, and along this side is Ryukyu Trench. And she said the disaster happened here. She indicated this is a volcano eruption. And the volcano eruption will make huge tsunami. The tsunami will attack Japan, Taiwan, and the Philippines. And then she also mentioned that there are two dragons flying from the air. So a lot of the news reporter asked me what happened to this one. Is this true? Will this event, this prediction come true? And I would say yes and no. Let's say no first, because this comic book predict that the huge event happened in the Philippine Sea Plate. The Philippine Sea Plate located right here, just like what she drew. But from the Earth science point of view, the large earthquake or large tsunami will never happen inside the continental plate. The large mega tsunami or mega earthquake always, I can use this very strong word, always happened around the trench area, that the collision area line between the continental plate and another plate. For example, here's the Euro-Asia plate, and here's the Philippine Sea Plate. So if she says something happened around this plate, then I would say, yeah, maybe possible. But she said the big event happened right in the middle of the plate, and I would say no, based on the modern science acknowledgement. There's no any clue says a huge event might happen here. So and then the news reporter asked me, then how come I say maybe the answer is possible? I would say because she is not a professional earth science people. She's not a scientist. She's just a young girl 30 years ago. So when she was a young girl and 30 years ago, by the time there's no cell phone, there's no internet. There was internet, but not so popular. So I asked the news reporter. I say, if so today you listen to my talk, and after the talk, then can you write down all the details for what I said? And she said, no, it's impossible. So I say, that's right, yeah, because she was in her dream, and in her dream, and she drew something might have something wrong, but I can sure that she dreamed some disasters, and beside Taiwan and Japan, that's for sure. But for details, it might have some errors. So then she say, can I say some more details? And I say, before I was talking about the details, I want to introduce one famous model, which is the focus of today's presentation. That is a very famous numerical model. It's called Concord numerical model. Concord is Cornell multi-grid coupled tsunami model. It's developed by my advisor, Professor Philip Liu. And this model can solve shallow water equation on the spherical coordinate system, and also can we use a very coarse grid and also very fine grid, because this model can use multi-layer. And this model can also being used for calculating the tsunami inundation, which is very important for the coastal area. So, so this model has been widely validated. For example, this one I just choose some of the famous case validation case. One famous case is the tsunami run-up. So this run-up case is done by another famous tsunami expert, Professor Cassis Sinolakis. When she was a PhD student, he did it, sorry. And the data are presented on the NOAA website, as you can see here. So when the solitary wave or tsunami came in, then the wave will come up and goes down. So here shows the results for numeric for laboratory data, and the solid line is the Comcast simulation. So you can see that the result is quite good, but I would say, of course, because it's being chosen. Because Professor Philip Liu chose this one as a benchmark problem, so the result must be good for Comcast. And then when I came back to Taiwan about 20 years ago, then I bring this model back to Taiwan. And by the time there was no like the 2004 South Asia tsunami just happened, but the 2011 Tohoku earthquake haven't happened yet. So I have plenty of time to run by using Comcast to simulate the 2004 South Asia tsunami. And I realized the Comcast is really accurate, but very, very slow. So I cooperate with people in Academia Sinica to speed up the Comcast model. And so they help us to improve the Comcast to be a multi-core model. So this picture shows that I was in Singapore, and they purchased a very by the time it's a modern computer. So I have a chance to test this model by using multi-core. So you can see that we test only 32 core server in NTU. I remember the one machine cost $30,000 US. And I was a poor PhD graduate student. So by the time I feel very satisfied, because the machine worked very hard, and the CPU runs 100% almost. Then when this model was done, Tohoku earthquake happened. So we spent about 20 minutes to prepare, or I say waiting for the fault parameter. And for our new version of Comcast, only spent 1 minute to finish the tsunami simulation from Japan to Taiwan. So it's more than a real tsunami simulation. And this one also, it not only is very fast, but also very accurate. So we compare our result with, so this is by the time it was the first version of Tohoku earthquake's tsunami simulation. So you can see this is still, I didn't change anything. This is the first version for tsunami simulation. And the tsunami the second layer is that tsunami propagate toward Taiwan and hit the east coast of Taiwan and move north and move south. So I compare our results to the gauge data after the event. So here I choose some of the comparison. Here you can see that there was a Japan tidal gauge station called Hanasaki, and it's around this area. Actually, Japan has a lot of tidal gauge, but most of them destroyed by this mega tsunami. So Hanasaki is the one one gauge which have very complete data. So you can see that this on this figure, the black line is the observed data, and the blue line is the simulated result. So the comparison is very, very well. How can I say this one is very well? Because this is a very large scale earth science problem. Earth science problem usually 100% error or 200% error is acceptable. But as you can see, this one, this is almost less than 10%. So this like just like our I would say our tsunami scientist, the dream of our tsunami scientists, because this accuracy is more than what we expected. So it's quite accurate. So we are not satisfied only compare with one tidal gauge station. We also want to compare our result with different sources. So we choose the other one is the NOAA buoy. So USA have NOAA has deployed a lot of deep ocean buoy to receive the tsunami signal. So this is NDBC and very the northern part of Japan. So you can see that the comparison also shows very good results. And then we compare our results with, we even very brave, compare with the result with Russia tidal gauge station. So on the opposite side, or west side of Japan, please remember, please notice that the Tohoku earthquake happened on the east side of Japan. And on the west side of Japan, they also received some very weak signal. It's about 15 centimeters only. So we also compare our results with that. So there's a very weak tsunami. Almost, it's like cheating. I say the result is so beautiful. Okay. So then it's very nice. So we have confidence to compare our results to Taiwan. How come I show the results in Taiwan for after all the comparison? Because the tsunami wave propagating from Japan to Taiwan have to go through all the Ryukyu change, and the Ryukyu change is very complicated. The ridge in the ocean that will make the numerical simulation very difficult. So here I show you the results, the comparison result. You can see that there's a 1, 2, 3, 4 gauge comparison, and also the black line is the observation, and the blue line is the simulation. So you can see that the result is very, very nice. So that gives us very good confidence that we can make the simulation fast and very accurate. That's why by the time I was quite popular because our government want me to provide more information about the future potential tsunami hazard in Taiwan. And also a lot of media want me to say about the tsunami. So before that, I want to show you something about how to connect our tsunami simulation with the ionosphere technology. Because I noticed this talk is arranged by Tso PRISM. At the beginning, I thought Tso means tsunami, but later on I realized Tso means Taiwan Space Union. Okay, so Tsunami or Tso PRISM, all good to me. All right, so let me see. So this is the work done about 10 years ago, actually, with Professor Tiger Liu, Liu Zhengyan. So he said, maybe we can try to see something from the sky. The ionosphere might be disturbed by a large scale motion, for example, like tsunami. So I say, okay, sure, let's try this one. So then I asked her how to know the ionosphere being disturbed. He said, easy. We can use a GPS signal. And I say, why GPS signal can can let us know the tsunami disturbance. He said because the GPS signal will affected by the ionosphere. If the ionosphere have some waves in there, then the GPS signal will become very unstable. Then after taking the best results, so the unstable signal can be isolated out, and this signal might be the tsunami signal. So we show this. So we starting working on this one. So here shows a cartoon showing if there's a tsunami, then the ionosphere will be affected between the GPS satellite and the GPS receiver. So here is the result by the time. On the left panel is the one I use the numerical simulation, and on the right panel is the field the tsunami signal from the ionosphere. So you can see that the tsunami signal really captured by the GPS data. So here also shows some results for stationary pictures. So for example, like after the 10 minutes after the earthquake event, so I refer 10 minutes as the early stage of the earthquake. The ionosphere signal contains both seismic and the tsunami waves. So here is the tsunami, and here has two signals. One is the seismic wave, one is the tsunami wave. And 20 minutes after the earthquake, seismic wave rapidly propagate outward. But the tsunami wave is so slow; it's only about like 200 meters per second. Okay, compared with the like earthquake, the propagation wave. So and then 1 hour later, we can see that very beautiful result, which is the tsunami gravity wave propagate outward. And 2 hours later, okay, the tsunami wave towards Taiwan. So if we go back to take a look at this one, so you can see that at the very early beginning, there's a shock wave suddenly move out, and then followed by a regular, slower propagation tsunami wave. So maybe we can use this method to do the tsunami early warning from the ionosphere. Okay. So this is a very interesting topic. All right, so let's go back to our Ryukyu change. So before I starting working on the Tohoku earthquake, actually I already show people this picture. This picture is provided, not me, provided from USGS in 2006. So this picture shows that there's a line, black line. Those black line means the change. So change means the boundary of the continental plate. So here's the Euro-Asia plate, and here is the Philippine Sea plate. So as you can see, along this change, there are some errors. The errors means the speed and also the direction of the continental plate. And the arrow colored in somewhere colored in blue and red and something like this one. So here shows that USGS says that if this one is colored in red, that means it's have very high probability to generate a hazard. And so if we take a look at this picture, you can see actually in 2006, 5 years before the Tohoku earthquake, USGS has already given a warning. That means they say here they might have a huge earthquake and also tsunami. Then 5 years later, it really happened. Unfortunately, by the time Japan government didn't pay attention to this one. So after the 2011 Tohoku earthquake, they pay a lot of attention to the second red arrow. The second red arrow is the Nankai Trough. Okay, so Japanese government is so worried about the Nankai Trough. But for Taiwan, I think people should worry about first is Manila change, and the second is Ryukyu change. Okay. So why is that? So in 2008, 2007, I published 2 papers, and that make people very nervous. The paper says that Manila change actually might generate gigantic tsunami, then that will seriously affect Taiwan and also Philippines and also Hong Kong and also Vietnam. And I also from the GR law. GR law give us a relationship between the earthquake magnitude and the annual rate, which is a return period. So this result shows that for Manila change, the return period for 8.5 is about 200 years. For return period, about 9.0, where earthquake magnitude 9.0 is about 667 years. So I hope you have some idea about the earthquake magnitude. For example, for like Tohoku earthquake, the earthquake magnitude is about 9.1. And so if we say, okay, Tohoku earthquake is so dangerous and so large, then from this figure, from this table, does that mean we are safe from that kind of large earthquake? Because it takes about 700 years to have such an earthquake. So in my paper, I say no, because Luzon Island actually colonization by Spanish people in 1560. So from 1560, they have write down the diary to put down something like, okay, the dogs are farting, fighting, not farting. Barking, okay, and somewhere have sometimes there's a fire, okay, and the earthquake, and like small tsunamis, and somebody are arguing. They will write down the details on their diary. But so we check the diary. Actually, there's no such thing as huge earthquake or huge tsunami happen. So from 1560 until now, it's more than 450 years. 450 years actually is the earthquake magnitude can reach to up higher than 8.5 and reach to 9.0. But we don't know what happened before the Spanish people colonized the Luzon Island. We don't know what happened. So actually, in terms of the return period, the earthquake has already reached to about 8.5 to 9.0, and even higher than 9.0. So in that paper, I gives a lot of evidence saying the earthquake actually, the energy of Earth, the continental thrust, the energy accumulation actually is very large. Another improvement is came from the GPS measurement. The GPS measurement says that the continental plate movement is about 8.9 centimeter per year. So in terms of 8.9 centimeter per year and for accumulation for more than 440 years, the strength is about 38 meters. I hope you know how large the 38 meters is, because for 2011 Tohoku earthquake, the slip, or we say the strength was about only 25 meters. So actually the accumulation is beyond the 2011 Tohoku earthquake. So I say maybe we should really focus on this one. So I show people the scenario I created. So this is the result of the tsunami result from that paper. So I say the tsunami will, the Earth tsunami, I assume that was 9.0 earthquake generated tsunami. So the tsunami will attack Hong Kong, Macau, and also parts of Taiwan. So this is the simulation from that case, from that paper. So here is southwest part of Taiwan. We say Kaohsiung is here, Pingtung is here, and the Tainan is here. Is Xiaoliuqiu, and the tsunami wave come and go. So they have positive wave colored in red and the negative wave colored in blue. And so that make Hong Kong government very nervous. So they have lots of interview with me and ask me how to do something for this Earth tsunami. So, and also we from the in Taiwan, we also have many other historical earthquake, and for example, like 1867 Keelung earthquake. So actually, from the in Taiwan, I by the time I realized that people usually say Taiwan has no tsunami event. Actually, it's not. There was a lot of tsunami. So our government, Taiwanese government, want me to tell people more about the tsunami. So they give me a project, asking me to evaluate what's the tsunami hazard in Taiwan, and this one is related to today's topic. So I did a big project and create 18 change type tsunami and 4 fourth type tsunami. So this is the most important results from that project. This result shows the tsunami scenarios, and the result actually has the legal power. So the government has to follow the results. So so we have we have many discussion with earthquake experts and also geology experts. I asked them to pin down the potential largest earthquake around Taiwan. So you can see that this is the potential largest earthquake, and I numbered one. T1 means tsunami 1. T2 means tsunami 2. So 1, 2, 3, 4, and until 18. And each one has the earthquake magnitude. So starting from 8.1 and end at about 8.8 and 8.7 something. So as you can see, this is actually surrounded by the Philippine Sea plate. And this part is the Ryukyu Trench. And this one is Nankai Trough. So let me show you some of the results. And so when we do the tsunami simulation, the one important thing is the numerical grid. Bathymetry data. So our national president asked the military to give me the very detailed topography and the bathymetry to run this case. So you can see that in this case, I use 6 layers. And the first layer is about 3.5 kilometers. And the finest layer reached to 2 meters. So again, with this detailed bathymetry data, actually is also like a dream for doing tsunami, because you can really do something very nice. So let me show you some of the results. The first one is T1. I would say the east side of Taiwan. So this is called the maximum wave height, the map of maximum wave height. The map of maximum wave height shows you have paid more attention on the coastal area, not in the deep ocean area. The coastal area, if they're colored in red, that means the tsunami high is higher than 5 meters. So let's see the results. So this is the T1 offshore Hualien, or we can say this the last part of Ryukyu Trench. So this T1 caused a lot of damagement on the east side of Taiwan. And the T2 is notorious Manila Trench. So you can see the Manila Trench will directly hit Hong Kong, and this part is the nuclear power plant in mainland China. We say 大亚湾核电站, okay? And also this result shows in Taiwan, the southern part of Taiwan is under the serious threat for this case, including our nuclear power plant and Pingtung and Kaohsiung. And the T3 also hit the Hong Kong, Macau, and the nuclear power plant from the mainland China side, and also Taiwan, the southwestern parts also under the threat. And then we go through number 4, number 5, number 6. So number 6 also will affect Japan and not Taiwan. And the number 7 is very interesting. This one is facing the eastern side of Pacific Ocean, but Japan is also colored in red. So it's quite strange that the tsunami going this way, but Japan will also be affected, but Taiwan is not. Then number 8. So number 8 is the case of YAP change. You can see that in this case, actually the tsunami energy directly project to Taiwan. So Taiwan will seriously damaged by this case. And also Philippine Sea plate, and also the island chain between Taiwan and the Philippines, and also the entire Japan is colored in red. So I have to stop this one for a while because in this case, it's almost satisfy the Miss Ryu 龙树亮小姐. Because from in her dream, the disaster, she said, is from Japan to Ryukyu change to Taiwan to Philippine Sea plate to Philippines, and also the island exposed. So and also this tsunami also passing the center of Philippine Sea plate. So if people ask me, is there any case that very similar to the dream, I would say yes. One of the case actually almost satisfy most of the situation she said, but this one was not caused by volcanic eruption. This one is caused by mega earthquake and the mega tsunami. So as I say, I'm not sure if the Miss Ryu is 龙树亮小姐. Miss Ryu really documented all detail correctly, or she made some mistakes. Otherwise, this case might be one of the candidates to satisfy all the situation. Okay, so let's keep on working on. Now it's T8 and the T9. T9, you can see slightly different location than the tsunami wave will leave Taiwan and facing the Japan. And the T10 and the T11 and the T12. So you can see that no matter which case, Taiwan, most of cases are safe because they're colored in only light blue or light green. But Japan always colored in red. In red. So I say tsunami just like tourists. They like to go to Japan. They don't like to go to Taiwan. Okay, so and the T3, T14, T15. T15 is the Nankai Trough, and the T16 is the Ryukyu change, and the T17. And starting from T17 and the T18, Taiwan will be seriously, again, affected by Ryukyu change. So here I show some summary of the result. So it shows that T1, T2, T3, and the T8 will have a significant impact to Taiwan, but also T18 from Ryukyu change is also will have important, significant result. So let's go back to the one I say from the Nankai Trough, because the Japan government also want to know what happened what might happen to if Nankai Trough really creates a huge tsunami. Then this is the simulation result. So thanks, Xinyi, for doing this simulation. So you can see that tsunami propagate and first hit hits Japan and reach to Taiwan. So here's the detailed tsunami propagation to Taiwan. So this color shows about this one. All right. So actually, the tsunami wave in Taiwan, the wave height is quite small. So this is the maximum wave height. As you can see, the most energy toward this direction, not toward Taiwan. So Taiwan actually only Yilan and Suao has to be very careful about this case. And the arrival time shows that it takes about 4 hours, 3 hours to reach to Taiwan. And so 3 hours here and 2.5 hours, the first wave will come, and the 3 hours, the main wave will come. So here's all the tidal gauge from Taiwan. In Taiwan. So here, let me show you the final results of this simulation. So it shows that the largest wave is happened about 25 centimeters. So if something really happened, I would say, don't worry, it will be safe in Taiwan. But that pray to people in Japan, because Japan will serious damage by this earthquake and tsunami. So that's all. I want to say more about what I did, like mega tsunamis I have done, and the landslide tsunami, like rock type tsunami, slump type tsunami, mudslide tsunami, local scholar, there's a lot, but I don't have much time. But before I end today's talk, let me show more about interesting results for today. So starting from 2018, there was an earthquake happened. It's called Sulawesi earthquake, or what we usually call it Palu earthquake. So this Palu earthquake actually, the surface movement is, we say, is a horizontal movement, not vertical movement. So in terms of tsunami, this case shouldn't generate a huge tsunami, but the result actually is different from we expected. This Palu earthquake is only 7 point something, but the tsunami is quite large. So you can see that the tsunami coming from the ocean side, oh, huge, really huge. You see that? It's scary. Then also a lot of civilian cameras recorded the earthquake. Okay, you can see the earthquake happened, and then tsunami come. But that confused us because tsunami come way too early. And the other one is also this one, earthquake happened. Or you can see that it's a really scary earthquake. But in terms of tsunami generated earthquake, this one earthquake is just okay. But the tsunami, you can see, is coming, okay? And this case, very interesting. It shows the first time people really use a video camera to record the landslide tsunami. So you can see here's a landslide tsunami, and a lot of landslide tsunami, and the landslide tsunamis. And also landslide tsunami from the airplane. So also on the boat, people also see the landslide tsunami. Oh, it's huge. So from here, you can see the large landslide tsunami, and also 1, 2, and also here comes another tsunami, tsunami wave. This is smaller, okay? All right. So a lot of evidence shows landslide tsunami. So this refers to another huge event happened in Taiwan, which is last year on April 3rd. Hualien, we have a huge earthquake happened in Hualien. The magnitude is 7.4. Okay, I cannot say huge because compared to 9 point something, that's quite small, 100,000 times smaller. But this earthquake really damage our famous, we call Turtle Mountain, the head of Turtle Mountain, because that create a huge landslide. So this give me a motivation that we should do something about landslide tsunami. And also we found the tsunami borders in Taiwan. That might indicate we have a chance to reconstruct the tsunami events in Taiwan. Okay, it's related to history. And also this scour hole shows the tsunami borders shouldn't be this small. Originally should be much larger because of the ocean scouring make the swashing make the border much smaller. So, and also from the engineering point of view, the tsunami will make the foundation loose. So we need a good numerical model. So that's I create a numerical model, which I don't want to tell you the details. Just want you to know this model is very accurate, because this model is originally designed for NASA, from NASA to launch the rocket. So we use this model and the modify model to give the tsunami module. So this is the tsunami simulation. Okay, the tsunami simulation is very beautiful to me, and we can put whatever we want, like the pollutant going up, the pollutant being after the tsunami that will or a long wave that will give you a well mixed. And also we use this model to do the wind turbine simulation and the nuclear power plant attacked by a tsunami. So you can see that we connected with a large scale Comcast model, and so the tsunami waves coming in and flood over the water intake. And also we can do the simulation for the sloshing problem, because the sloshing problem will damage our nuclear power plant. Okay, so this is a beautiful result for shaking. So, but I need a moving solid module for rock slide tsunami. So my student Hu Shunkai, he helped me to create a very good model. It's called a rigid water method. So the rigid water model is coupled with DEM model, and here shows a very beautiful result. It's a floating box, just like a floating deck for the offshore wind turbine, and the comparison is very well. Also, the ball drop into the water and create a air chamber. And the benchmark problem want to see the air chamber. Okay, so these results give us very good trajectory prediction and the wave. So I here just show you something about the results, and also the landslide tsunami. Okay, very nice. So we use this model to do something very interesting. One is done by Huang Yixuan 同学. Okay. So this model shows we can really draw a solid material into water or elastic material into water. Okay, even though I don't know which from the earth science point of view why we need this, but we can do it. Okay, and it's probably the most powerful model in the world. All right, then we use this model to study the Greenland landslide tsunami. So the Greenland landslide tsunami happened in 2017. So this is the simulation because the wave height is quite large. So this is the simulation. Okay, nice and beautiful. So from this simulation, it shows the tsunami height is about 80 meters for landslide tsunami. All right, so we use this model to do lots of simulation, and also use this model to do the tsunami border simulation. So you can see that tsunami, we use a sphere to indicate the tsunami border. So when the large wave came, then this border will be pushed by the tsunami wave. So a lot of details I don't want to show you because we don't have much time. So let me show you some of the final interesting results. Okay. Okay, let's go back to the landslide because Yixuan spent a lot of time doing this. So this is the original shape of our Turtle Mountain is the shape after the earthquake. So some of the material just sliding down. So this is from Tasa. Okay, so the original one and after the earthquake. So we try to do the simulation. So this is the simulation result. You can see a very small wave coming to the right hand side, and the wave actually was 20 meters. So you can see that reached to 20 meters. So if the wave is not facing to the south, because the wave actually goes this way. If the wave facing to the Yilan area, then that will give us trouble. So why do we say that? Because this is a beautiful picture of the Turtle Mountain, okay, Guisandao. And there was two volcanic mountain. One is here, the other one is here. But this one has experienced a huge volcanic eruption. So you can see that this until today, there's lots of energy released from this area. So if you go to the opposite side, we can see there's a huge landslide happened before. So if we check the ocean bottom, we can see that actually there's some evidence showing actually the Guishan Island was erupted, and a larger landslide happened in that event. So this shows a very clear detail. So we use this model to use those information and run our model to see the tsunami generated by that case. And so this is the final result. And so that means in the future, if the volcano erupt again, the only possible tsunami direction will face to the Yilan area and cause serious damage. All right, I think that's it. And I should stop now because I'm running out of time. So thanks for listening.
Thank you very much, Wu Lao Shi. It was a very interesting talk. And then I have just one professor and two experts from Yilan, and they are listening to your talk very, very carefully. You know, any questions from the audience?
Yes. Okay, please can you hear me?
Yeah, please.
Yes, Professor Eric Lossa from Singapore NTU. Congratulations for your talk, very insightful. I would like you have presented a major tsunami with models which happen at the trench, right? So not really on the continental plateau. My question would be, is it existing models where we might have seamounts, intraplate seamounts, means on the continental plateau, that could have some landslides that could generate some tsunami? Of course, not of the same magnitude, but my question, I would be curious to know if there are some investigations.
Sea mountain, or are you saying sea mountain?
Yes, absolutely.
Okay. Yeah, sea mountain actually, there was evidence showing that a lot of earthquake actually generated unusual tsunami, and the unusual tsunami came from the sea mountain landslide. So as for the sea mountain landslide, the feature of sea mountain landslide is that the wave height locally will be very, very large. For example, like 20 meters, 50 meters, or the largest sea mountain landslide will be about like 50 meters or even large. And where can those sea mountain landslide happen? Maybe I can share my maps. This is using online, the benefit of using online. Okay, let me show one page. Hold on a second. So as you can see, actually, we noticed that like here, we have historical events, and the paper we published also shows that there's caused by sea mountain landslide around this area. And the other one is the Shiyuan Dao. Okay, our result also shows the Shiyuan Dao has a very large earth landslide tsunami, and push the mountain to push the tsunami border to about 80 meters high location. And the major cause was not the earthquake, was also caused by the sea mountain around this area. Okay, around this area. And the other one is the Keelung earthquake in Taiwan. We also found that the earthquake, the tsunami, might caused by the landslide around this area. So as you can see, that sea mountain is that landslide generated the tsunami is very quiet, very large, very dangerous. So if, for example, like in Singapore, okay, Singapore basically is safe from the earthquake, but we still need to be careful about the sea mountain landslide to see if there's a landslide, because you can see that Singapore, right? So if some like mountain which is unstable might really generate a small tsunami, and but basically Singapore mostly, I would say, is quite safe. People around this continental the change area should be careful about not only the change type of tsunami, but also should be worried about like the landslide triggered by the earthquake.
Yes, thank you. Other questions? Okay, maybe let me ask one. So you have simulated more or less almost all possible cases of generating tsunamis, but there's one case perhaps you could also try, which is with an asteroid hitting the ocean. Have you tried that?
Oh, my model can do that, but I haven't tried. Yes, thanks for Professor Wing Yip. Because from the prediction, she said actually happened in the middle. And one possibility to me is from the asteroid hitting the Earth, hitting the ocean. Yes, yeah. And once if the energy is large enough, maybe that will give us a huge tsunami, and also will disturb the currently stable continental plate and make a huge tsunami. So I haven't really tried it, but from the simulation, as I showed you before, we can do the ball dropping into water and generate bouncing back lots of waves. So for that case, then I think we can really do it. But the difficulty might come from the very high speed impaction. Okay, but I think we can still do that. Yeah.
Okay. Is that Lanza? Do you have a question?
Yes, I have a second one if nobody else wants. My question is dealing with the South China Sea. If I'm not wrong, geophysicists have found south of Vietnam seamount, a volcano, which is underwater, and it's more or less shallow water. I don't know exactly the depth, but something like 200 meters or something like that. Is there a chance, and I'm not very sure about the bathymetry knowledge in this region, is there a chance that a slide of a part of the volcano, of the underwater volcano, is creating some tsunami for affecting the South China Sea neighborhood?
Okay. Here, actually, the volcano can only happen here. I think inside this area, there's no significant or large volcano eruption, no possibility. Another possibility come from this area is another continental, the age of continental plate. So in terms of volcano, I think if I would say actually the scenario might be very close to the one I say the Mandela Trench, because most of the volcanic around this trench area. So if that really happens, then I will expect a very high possibility that will caused by the earthquake and also trigger another volcano eruption. But in terms of Vietnam, we have done many we have done many studies, and but focus on the from Guangzhou this area, because from his historical record, it says there's many huge earth tsunami happen, and the huge tsunami might come from this area, and also might come from this kind of slope. Can you see that the slope actually there's a very steep slope. So this steep slope is very close to the Vietnam. So if the slope really is generate tsunami, then of course the Vietnam will be affected by that. But I would say to study this the very near shore tsunami, we need a very high resolution bathymetry. And high resolution bathymetry usually is the confidential data for each country. So I have students from Vietnam, and I will give them this homework to try to study those possible cases. Yes, thank you very much.
Thank you.
Okay. If there are any other questions, there's Lin Jinhua. Yeah, please go ahead.
Forgive me, I just use Chinese.
好，
老师，对不起，我注意到您说那个南海海潮的海啸到达台湾东岸的水位大概是30-40公分，这个我应该没看错了啊。
没错。
那问题是我的concern是这样，就是说台湾的东岸有很多的港口，包含苏澳军港、花莲港，还有一些大小不一的渔港。那我们也知道说，从日本那个3·11海啸，我们发现说海啸到达近岸，那个会跟近岸结构，特别是港口跟会沿河川溯上。
对。
那东部地区也有很多，其实在比如说像宜兰立泽那个地方，就有很多那种大小不一的灌排渠道。
对，你那边在做嘛，对不对？
灌排渠道，那这些是不是因为30-40公分说大不大，说小不小，但是对于一些港口还是有它的影响，毕竟那几个大港都是有大型的这些船只，或者说在内陆地区还是有一些居民会在。那不晓得这部分会不会有，就老师您的评估会不会有实际的影响？
好的。Okay, thanks for Dr. Lin. Let me briefly introduce, translate the questions. He said, as I say, the tsunami from Japan, actually, even though like the Tohoku, this kind of large tsunami, when they reach to Taiwan, the tsunami high is less than 50 centimeters, as I say, around 30 centimeters. So, but however, there are a lot of fishery harbors and very like a local irrigation system, which are with very low elevation. Will those 30 to 50 centimeter tsunami affect the area? I would say it's really hard to say the details, because we need to consider the detailed simulation. But I would say from the result, it shows, you can see here is Yilan. As I say, actually Yilan is more dangerous than Hualien, because Yilan is very flat, and a lot of the river or irrigation area actually is very close to the sea level. And not to say one important harbor is called Suao is located here. So if the tsunami came and with that kind of large earthquake, that means the tsunami wave length is very, very long. So the 30 centimeter wave length with very high resolution simulation might shows, I expect, might give some damage to this one. So actually I have another project doing this. That kind of project is saying that, okay, so from the tsunami from Japan, like it takes about 3 hours to reach to Taiwan. So we have time to escape. And also we have to know how far those ship or those boats should escape from the tsunami. Because the tsunami is called tsunami because the tsunami will attack harbor area. So those areas mentioned by Dr. Lin actually is quite thoughtful because they should move their boat to the deep ocean area. Okay, and but how far they should go, that's one of the questions. We are still working on this. Very good point. And for the people in the inland area, for 30 centimeter to 50 centimeters, I think we can just move to the second floor or third floor of the buildings, then that will be safe. But as for the property damagement, I think just let them go. Okay, that's my answer.
Okay.
Professor.
Yeah, I mean, if you have further questions, you could always write to Professor Wu, right? You could find his email address very easily. Or check the NCO web page. Okay, good. Now it's almost time's up, and I want to thank Professor Wu for giving us a very detailed description of his work, and I think it's fantastic work, excellent work, and keep working. And,
thank you.
I think that's wonderful. In that case, I would then close this seminar. And thank you, everybody. Thank you, everybody. And thank you, especially to Professor Wu for his lecture. Thank you again.
Thanks, Professor Wing. And thank you everybody for listening.
Yeah, bye-bye.